So today we have two lectures or two different topics. One is the continuation of what we started before on learning from a stream of data and value function learning, essentially. And the other part would be on value function approximation. Last part we talked about different methods like Monte Carlo estimation, Q-learning. We talked about stochastic approximation as a way to estimate some quantity based on some noisy data. And we saw Q-learning algorithm, so I don't go through it. So this is just Q-learning that you can see here, which had update rule that looks like this, that essentially we update qt plus 1 for the state and action that we observe at time t based on the previous value and some time plus some learning rate times reward plus gamma of maximum of qt at the next state, xt plus 1, and maximum is our actions. So this is for the observed state action pair, and for the others, we don't change the value, which is equivalent of having a learning rate of 0 for them. Okay, so this is kind of the full algorithm. We talked about what Q-learning, what policies Q-learning is actually evaluating. And we had this discussion that it is evaluating the greedy policy of Qt. So it would be pi of greedy of Qt. So that's effectively the policy that is evaluating, and this makes it an off-policy sampling scenario or an off-policy algorithm, which means that we're following one policy which is different from the policy that we are evaluating. Okay, so another algorithm that is commonly used is called SARSA. And this is based on more like a policy iteration type of algorithm. If you go through why it is working or how it's working, it looks very similar to Q-learning, but comes from a bit different kind of argument. So remember that policy iteration was the case that we have as we estimate some value function, like action value function for a policy pi, and then after we have that estimate, we improve it. So that's policy iteration. And if we do this many times, it converges to the optimal policy. So we had, I guess we proved that result, and we proved that it actually converges in a finite number of times, in a finite number of iterations. So this is great if we know the model. So, but what if we don't know the model? If we are in the reinforcement learning scenario, that we don't know the model, what can we do? So one idea is that we'll try to mimic the usual policy iteration by the tools that we have for learning. And one of the tools that we have in learning is temporal difference learning, which is a kind of this method that you saw that we can use in order to estimate the value function using our current estimate of the value function. So the way we can do it is that, well, one way, this is not the way that we should do it, but if we want to mimic policy iteration, we start, so I say the usual policy iteration, waits long enough until the TD method produces a Q that is converging to Q pi. So if we wait for long enough and we have set the sampling, the step size properly, and we have proper sampling distribution, Q converges to Q pi, Q that's obtained by TD. And then if we do that, we can then improve the policy by computing the greedy policy with respect to Q pi. So what is the problem with this approach? Any suggestion? So how long does it take for Q to converge to Q pi? Okay, let's see what's happening in the chat. Well, it is inefficient, but what I want to kind of think about is that the duration, how many iterations we have to go on, how many samples we have to go. If we want to have exact convergence, like get Q that is exactly like Q pi, we have to wait for infinity. Because Q learning or TD learning, not Q learning, TD learning converges to Q pi, but only asymptotically. So we have to wait until infinity before we evaluate Q pi. And then after that, we can improve the policy. So this is, as you said, it's inefficient because we don't have many infinite times. So the other idea, so this is not a good idea, but this is a way we can mimic policy iteration with combination of TD and just the usual policy improvement. The other approach is that's called, is basically, maybe we don't need to wait until infinity before start improving our policy. Maybe we just have a kind of approximate estimate of Q pi, and then start improving the policy. So the idea is that, okay, we get a Q, which is kind of close to Q pi at iteration K, say, but this is only approximate. But then use that Q in order to improve a new policy. So say new policy, we assign it to be the greedy policy, but with respect to this Q, which is not still Q pi. So we just have an approximate estimation of Q pi, of Q of pi k, but then improve our policy. And then do this again. So then after that, we have another pi, another Q, which is kind of only approximately equal to Q k plus 1. So this is, excuse me, this is called generalized policy iteration, or optimistic policy iteration. And the basic idea is that we improve the policy before Q converges. And this can be shown that this is also a reasonable approach. So this is the basis of SARSA algorithm. So it is a policy iteration or generalized policy iteration type of algorithm that uses TD for estimating the value function. Okay, so let's see if there is a question. Yeah, okay, so I guess that's it before. Depends on the number of states. So SARS algorithm is very similar to Q-learning. So we start at state xt. Then we choose an action according to some policy pi t. And I'm going to specify what that policy pi t is. But it is just the policy for now. Then we go to the next state and we get the reward by following that policy. And then at the next time step, at t plus 1, we choose action at plus 1 according to the same policy. So it would be, action would be pi t of xt plus 1. And then the update rule is like this, that for state, we update the qt plus 1 at the new time step at states xt and at according to the usual stochastic approximation update rules that we had seen. So it would be essentially 1 minus learning rates times the previous value of actual value function at that state. So that's the as before, plus learning rates, alpha t xt at, times reward plus gamma times qt of xt plus 1 and at plus 1. So what is kind of important here is that this at plus 1 is the same at plus 1 that is here, so which is selected according to pi t. Okay, so what is the difference of this with Q-learning if you compare the update rule? So
this one is an online on-policy algorithm, sorry.
that's an on-policy algorithm, that's right. But if you look at the update rule, what is the difference in the update rule? So I go back a few steps, slides. So everything looks the same except which part?
It's not taking the max action, it's taking the policy choice.
Yes, exactly. Yes, so it is not taking the max, but it is computing, like, instead of max over A prime, it has AT plus 1, which is policy T xt plus 1. So this would be for SARS. So that's the kind of the difference in, and also there's this comment that that's not greedy. Yes, that's, it is just policy pi t, but it's not evaluating the greedy policy. So that's a difference. I'm coming back to this just in the next slide, but maybe I'll talk a little bit about the policy, what is policy pi t should be. I mean, it can be different things, but the usual way is that we want to kind of follow the policy iteration type of algorithm. So we want to do some kind of generalized policy iteration, which means that we want our policy to be close to the greedy policy or the greedy policy of the current estimate of the action value function. So what we choose is that we choose pi t to be close to a greedy policy pi greedy of q of t, but with some amount of exploration. So we may choose epsilon greedy policy with respect to qt. So we can choose it epsilon greedy policy of qt, but we can also do it different ways. Like we can have, I think I talked about the Boltzmann distribution. We can also choose the Boltzmann distribution for choosing this policy. So the intuition here is that the greedy part performs the policy improvement, and then the occasional random choice of actions allows the agent to have some exploration and kind of go, basically enables it to estimate the value of actions that it hasn't seen before. And also allows it to go to regions of the state space that it may not go otherwise. So I think we talked a little bit about exploration before, that, like I guess in the immediate reward case, if we don't have exploration, what might happen? Okay, is there a question about SARSA? Okay, no question. So why the name is SARSA? Do you know why it's called SARSA?
State action, reward state action.
Right, exactly. Because the quantities that it uses are essentially state. So we have state here, we have action, and then we get reward. And then next state, S, and then here we compute another action. So that would be SARSA. If we used, instead of X, we use S for state, that would be even more clear that. So SARSA update uses ST, AT, RT, ST plus 1, AT plus 1. But we have X here, so. Okay, so that's the name SARSA. So one other thing, if you want to call, kind of using the same naming convention, have some other name for Q-learning, what it would be. So Q-learning, we have state, right? and we are set state S, we are again at state, and we choose action A. But then what happens? Do we choose next reward? Do we choose reward or next state? Okay, I guess it can be a bit more interactive, but I guess not.
Is this for the Q-learning, Professor?
Yes, I'm talking about Q-learning, like if you want to call using the same naming convention as SARSA, if you want to name Q-learning, what would happen for it?
So you receive an award and a state, and then you choose based on the greedy?
Right, so it would be, but so I guess the difference would be that we choose as action, reward, and action, but we don't choose the next action according to policy. It would be just the one that is selected by greedy policy, which is implicit in doing the max. So the name of Q-learning would be probably SARS instead of SARSA. But I guess we don't call that. Right. Okay, so that's the comparison of Q-learning versus SARSA. We talked about it essentially. Like if you compare the update rules, in Q-learning, we have maximum over actions. In SARSA, it is the action at the next state would be the action that is selected by policy pi-t. So that's a difference in how it looks like the update rule. But if we compare at level of evaluated policy, so Q-learning is, as you already mentioned, is evaluating the greedy policy, pi-g, but SARSA is evaluating pi-t, which is the same policy that selects actions. So SARSA algorithm follows policy pi-t and generates action according to, and evaluates the same policy. So it's on policy algorithm, whereas Q-learning follows some policy, but it evaluates a greedy policy. So these are not necessarily the same. Okay, any questions so far? Everything's clear? Okay, so I think the next step is that I want to prove why Q-learning converges. And for that, we need some kind of extra results in stochastic approximation. So I go back to stochastic approximation and have a second look at it in a bit more, perhaps a little bit more abstract formulation of stochastic approximation. And then I provide a result. I don't prove it, I just provide a result showing that when a stochastic approximation procedure converges in a certain sense, and then use that result for proving Q-learning. So stochastic approximation, if you recall, was, okay, so not stochastic approximation. Suppose what we want to do is that find the fixed point of an operator L. So an operator L, we want to find the theta that satisfies this fixed point equation. And suppose theta is a d-dimensional vector and L is a mapping or from RD to RD. So we can consider the iterative update. Like in order to find this, we could do, previously what we had was, we can compute it like this. And this was essentially converging when L is a contraction operator, right? Because of Banach fixed point theorem, we have this, that if L is a contraction, then theta t converges to theta star, and theta star being the solution of fixed point equation. We can also modify this procedure a little bit. And instead of this kind of maybe more, we can call it more aggressive update up here, we have this one instead. So we update theta t plus 1 as 1 minus alpha times, okay, so there should be t here. One minus alpha times theta t plus alpha times L of theta t. And alpha is, you can think of it as a step size or learning rate. So it can be a small number, like 0.1, say. So we compute L theta t multiplied by some scalar, small scalar, and then add it to the previous value that is kind of dampened by 1 minus alpha. And this would be our new theta t plus 1. So if L is Lipschitz, or if it's contraction, so it's C Lipschitz with C smaller than 1, which introduces contraction, and alpha is small enough, this would converge. So this is the convergence of it, similar to the convergence of this update here, of course with a slightly different rate because we added some alpha. But the procedure still converges. But suppose that we don't have, now I want to get to the stochastic approximation part of it. Suppose that we cannot compute L of theta t, because this operator L, we can't directly compute it, but we only have a noisy version of it. So this is the setup here, that we do not have access to LT, but only a noise contaminated version of it. So it would be, I write it as L of theta t plus some noise, eta t. And noise is, suppose the noise is zero mean noise. So it is in expectation, the noise is, say, it might have some conditioning too, but it would be 0. So it doesn't, in average, it doesn't change anything. But each sample of it might move us in different directions. So what we can perform instead is some update rule, which is like this, that we are effectively only observing this value. So we don't have L of theta. So if we follow a similar procedure, we are effectively computing theta t plus 1 as the previous value. Again, I guess I missed a t here. 1 minus alpha t times theta t plus alpha t learning rate or step size times the noise contaminated version of operator L being applied to theta t. Okay, so is this clear? Okay, so that's good. So this is similar to equation 1. Let's see if it works. Okay, so I think this, I had it somewhere. Okay, so the beginning, the previous lecture, we had this, we used the stochastic approximation to estimate the mean of some random variable. So Z was a random variable whose expectation is M. Yeah, I guess. So essentially what we had here is Z of t was M, the mean. And then this procedure, we discussed that, we didn't prove it, but we discussed that it converges to the true mean. We actually showed that in expectation, it has the right expectation if with a fixed, say, alpha. So I think we had this result. Yes, so I guess we had this result that theta t in expectation of it converges to the true mean. But then we had this discussion of the variance, and we discussed that if the variance is if the step size is constant, then the variance would not go to 0. So, and then we had these two stochastic approximation conditions saying that if we want the learning rate, if we want that our estimate, theta, converges to the true mean, we have to satisfy this condition, stochastic approximation conditions, which is basically saying that learning rate should go to 0, not too fast, but not too slow. So this is a stochastic approximation for the case of estimation of a mean. But for estimation of, now here we are talking about a fixed point equation or an operator, and we want to find its fixed point. And we are in a similar situation. Okay, so, and as I just mentioned, if we have if alpha t is a fixed number like alpha for all iteration, the variance of the estimate would not go to 0. So we need some kind of steps condition and step size, which is going to be the usual stochastic approximation condition. Okay, is this clear so far? Any question? Okay, so we are, so this is a more kind of, so yeah, this equation describes how stochastic or how we can possibly find the fixed point of an operator L when it is noisy. We want to use this framework, something like, or at least something like this, in order to analyze Q-learning. So we need to have a kind of a bit more general model in order to analyze Q-learning. So let's talk about the general model. So at time t, this works like this. Again, we have a same operator, same theta with dimension d, for example. But at time t, we only update the ith components of theta t, and we don't change the other components. So we select some I in some way, random or not random, doesn't matter. And then what the update rule is only for, so for theta t plus 1 at dimension I, so this is the ith dimension of vector theta, and theta, remember, is say d-dimensional vector. So the update rule would be 1 minus alpha t of I, so step size for dimension I, times theta t of I, plus learning rate for time t and for dimension I, times the noise contaminated version of the operator, and then which we only observe the ith dimension of it. So this L, so this term, so it's L theta t, so that would be, L theta t would be a d-dimensional vector, but we only look at its ith component, so it only would be a scalar, plus a noise, which is for that same dimension. So this is, we only update one dimension, and the other dimensions we are not changing, which can be seen as having alpha t of j for j that are different from I to be equal to 0. Why? Because say if alpha j is 0, then we would have, okay, write it here, it would be like 1 minus 0 theta t of j plus 0 times whatever, doesn't matter. So this would be essentially copying j components that are different than I to theta t plus 1. Okay, is this model clear?
So at every time step, we only update one component. Is that kind of randomly chosen?
It can be chosen in any way, like randomly or in some way, doesn't matter. Okay, so let's see. So there's no question. So that's the model. So this is a kind of general stochastic approximation model, which essentially allows us to do asynchronous update. Like instead of updating all of thetas, we only update part of theta, one dimension of it. And you see the reason we want to do it is that because say, when we want to analyze Q-learning, we are only updating the Q value function of the current states and action, like xt and at. So you will, I guess maybe this is a good thing to have kind of mental image that later the way we are going to use it, I would be, okay, so theta would be equal to Q. So we want to associate theta and Q. And then we want to associate xt, at, state action that is selected at time t, with this index that is selected here. And then you will see that L would be associated with the Bellman operator. So that's the parallel. I'm going to talk about it. I have it on slides in it. I'll show it soon, but that's the kind of general idea. Maybe it's good to have it right now before we get to Q-learning itself. Okay, so we want to provide the results showing the convergence of theta t to theta star being the fixed point. And this requires some assumption, because otherwise, without any assumption, we may not be able to solve it. Okay, so assumption on noise. I guess one big assumption is on noise, like what is the behavior of the noise? Maybe it is clear here. I guess when I talked about this part, I said that the noise should be zero mean. So it shouldn't be a biased noise. It should be unbiased noise. And it is reasonable. If you always have a biased noise, then you are not converging to the same point. It's like in different samples from that noise, it is not going to cancel the past effects of each other. If, say, the mean of noise is always +5, you're always off by +5 in average. So the first assumption is the noise is going to be zero mean. I need to define some notation. I use something called FT, which is called the history of algorithm up to time t. So what does it mean? This is a variable that basically collects whatever happened to the algorithm from the beginning, time 0, time 1, to up to time t. So which includes like all the thetas that we have, theta 0, theta 1 at different time steps up to time t, plus all the learning rates. So alphas are learning rate. We can change it in some way. So that's a part of the history of the algorithm. And this is also all the noise that we have observed so far. So eta 0, eta 1, up to eta t minus 1. So up to the noise before we do the updates. So because we haven't, we are here at, we want to get theta t plus 1. We consider everything that happened until this particular observation of this L theta t plus the noise. So this noise, we don't know it. So this essentially keeps us the randomness at time t is not part of the history, but the randomness of the previous time steps is a part of the history. So what do we have here in this assumption is that if for all dimensions of theta and all time steps, the noise is, the conditional noise is zero mean. The condition is on the history. So if, for example, the noise is IID noise, then it doesn't really matter. It's not a function of history. If its mean is 0, then this condition is satisfied. So if it is IID noise, then this is, of course, it should be plus 0 mean. IID and 0 mean this is satisfied, but this condition allows noise to actually depend on history in some way. But so it's not independent from history. That's why we have this conditioning, but still it needs to be zero mean. And you see how it appears in, say, Q-learning. So this is reasonable condition. The second condition is a condition on the variance of the noise. So we have a norm, given any norm, there should exist some C1, C2, such that for all time steps and all dimensions, the variance of the noise, so this would be the variance, conditional variance, should be smaller than some constants, plus something that depends on the norm of our parameter theta. So if I only consider the first term, it says that the noise should be, the variance of noise should be bounded, which is, I mean, it's not unreasonable condition. If the noise has an unbounded variance, then estimation is going to be difficult. But it allows a little bit more than that. It allows it to grow the variance if theta t is become a large function. So if theta is a large vector, then probably everything might be amplified by something that is with the same size of, the noise also would be amplified by the same size of theta. And this is kind of, this assumption allows it to be depending on the squared value of the norm of theta. Okay. Any question? No question. Okay, so this is assumption on noise. We need to have a little bit of more assumptions, but I put them inside the statement of the theorem. So this is a convergence of the stochastic approximation. This is a result by Bertsekos and Tsitsiklis. So let's assume that this theta t be the sequence generated by that general model that I described. So it's a synchronous update. I update only one dimension of it. One assumption, okay, so assumption 2 is on the noise. These are the assumptions that I just described. So we assume that the noise satisfies assumption on noise. The other assumption is on step size. We assume that the step size satisfies the usual stochastic approximation conditions. So the sum of it diverges, but the squared value of it would be finite. So for example, if I choose A of t of I to be equal to, say, n of ti plus 1, and n of t and I would be the number of times up to time t. Oops. Up to t, that's dimension I, is selected. So essentially I have a, okay, so I have a counter on dimension I. I count how many times I have selected dimension I, and define alpha based on like 1 over that number of times. If I do these things, then the assumption would be, step size assumption would be satisfied. And there can be other choices too. Okay, what else do we need? Is the other that we need is that the mapping L should be a contraction with respect to the supremum norm, with respect to supremum or max norm here. So it should be a contraction, which means that if it give two vectors, theta 1 and theta 2, after applying them, they become closer. You had seen it before already a few times. So with right condition and step size, with the right condition and noise, and L being contraction, then theta t converges to theta star almost surely. And almost surely doesn't matter. And it's a kind of measure theoretic quantification of what is the meaning of convergence. But you can think of it, it is converging. So that's great. So theta t converges to the fixed point. So this is an interesting result because it shows that we are doing fine if we satisfy this condition. Okay, so any questions so far?
Yeah. When you say it converges to theta star, are we supposed to assume that's the optimality of
Yeah.
the fixed point? Because you can also converge to pi if you're using t pi, right?
Right. Okay, so I haven't got to Q learning or T pi, but yes, if we, this T star is this one. Okay, so.
We're just using that as a form of notation, whatever, right? Fixed point.
Yeah, so here I use a T star as the solution of fixed points. So that star is not related to the Bellman optimality operator.
Okay, just making sure.
Sure. Okay, this is good. Any other question? Is it right pace, too fast, too slow? Maybe I should do it. I finished this part, but only a few slides left. And therefore, next part, I get some feedback. Okay, so we want to use all these things was just to prove convergence of Q-learning. So Q-learning update rule has the same form of the stochastic approximation update rule. So, but with kind of some identification between terms of Q-learning and their formula for stochastic approximation. So theta in stochastic approximation would be Q. So Q is state action dimensional. So here we assume it is finite state and action. So it's a say 100 dimensional vector. So that would be theta. The operator L is the Bellman optimality operator T star. So the operator in stochastic approximation would be T star, equivalent of T star in Bellman equation. The index in the stochastic approximation update, the one that we update at time t, is going to be the selected state action pairs at time t. So xt, at, and at, that pair is the index I. And the noise term is going to be the difference between the true Bellman optimality operator applied to qt, so t star qt, evaluated that at xt, at, minus the sample-based version that we have, minus RT plus gamma max of QT, XT plus 1, and A prime. So that's the sample-based version of it. And this noise is essentially the difference between them. And it's clear if you put the equations in front of you and try to match these two things together. So maybe before I go further, what are the properties of, so what is the expectation of this noise? Is it going to be zero mean or not? Because we needed that condition, the noise to be zero mean.
Yeah, should be zero mean.
It should be zero mean. Do you have an intuition why it should be?
It's the greedy policy that you're following. And whichever should be the closest to T star.
Right. So it is, yes, it is choosing the same greedy policy that T star is choosing. And also it is like one kind of, it's a sample-based version of T star. I think I had it before, but let me get to this soon. And if it's not clear, we go back to one of the previous slides. But that's going to be zero mean. So we are going to verify the conditions of this stochastic approximation theorem. But before that, maybe what's the convergence result here? Suppose that, so I'm just saying the condition of Q-learning. Suppose that for all state and action pairs, the step size alpha t, xt, at satisfies the usual stochastic approximation conditions. And then also assume that the reward is of bounded variance, which is very reasonable. If reward is unbounded, has unbounded variance, then I mean, learning would be difficult. Then the result says that Qt converges to Q star. So Q learning converges, the solution of Q learning as t goes to infinity converges to what we want, the optimal value function. So which is a great news. Okay, so let's try to prove it. So suppose that at time t, okay, so there's kind of a lot of equations here. You have to go through it, but I just go through it once quickly. So suppose at time t, the agent is at state xt and takes action at, gets to xt prime, which is going to be the next state. So here just I'm using x prime to denote the next state. I don't use xt plus 1. And also it gets reward. So these are the usual things that we have already seen a few times. The update rule of Q learning is, what is the update rule? The update rule is, as usual, xt plus 1. We only update xt at. 1 minus learning rate for that state times Qt of that, plus learning rate times, okay, so update rule here is that t star Qt evaluated at xt80 plus a noise term. So I want to convert to the form of stochastic approximation. And the noise term would be, what is the noise term? It would be RT. So this is the noise term. It would be RT plus gamma max of something minus T star Qt xt80. So here you see that if I put these things together, if I add T star Qt plus this one, these two terms cancel, and only this sample-based version remains, which was the update rule of Q learning. So here I'm just having, but I just want to convert to the form of stochastic approximation formula. So this is the kind of the deterministic part, if you want to see it that way, plus the stochastic part, plus the noise part. And for the other state and action pairs, I don't change it. So we have a few conditions to verify. One is that the operator in the stochastic approximation result should be contraction, but we know that T star is a gamma contraction mapping, so it satisfies that condition. So condition 1 is assumed. What was the condition? 1 was, that's a condition on step sizes. So step sizes, we choose them to satisfy the desired condition. And then now we only need to assume, verify the assumptions on the noise, whether they are satisfied or not. Any question on this? Other parts? So actually, maybe this is a good point. Like, if instead of T star, I think as you mentioned, if instead of T star, we have T pi, so not, if instead of T star, we have T pi, we also satisfy this condition too. So this proof also works for just proof of convergence of TD algorithm for finite state and action, and not just for Q learning, but with only this change. Or yeah, I guess the rest would, the change of the rest would be very similar. So that works for TD learning too, but here I only prove it for Q learning. So let's think about the, so we had this, we need to verify the condition on noise. So FT be the history of algorithm up to and including when the step size alpha t xt8 is chosen, but just before the next states and RT are revealed to the algorithm. So the history before the noise in the current step. Then we have conditional expectation of this noise term at xt80 would be the reward plus gamma max q at the next state minus t star q pi. And this first term would be equal to t star qt xt80. So the whole thing would be 0. And to see this, I think either in one of the slides previously I had it kind of expanded, or you can take a look at the notes. But this is essentially t star qt has an integral, or it's an expectation. This is only one sample of it. So when we take expectation of it, that would be the same as the true expectation or the integral. So the noise is 0 mean, so that's great. Now we want to verify the variance condition, and that would be similar to, so I just write it eta squared. I divide it to just collect the parts on reward, like RT minus R of XT80 plus the term that is gamma times maximum of QT at the next state minus integral or expectation of max of QT at the next state. So this is essentially the expectation of this max. This is just one sample. So we have these two terms. And then this can be upper bounded by 2 times. So 2 times variance of reward plus 2 times gamma squared variance of this max. And yeah, I think this is clear. Maybe the only thing that might not be clear is where is this 2 come from? But I let you figure that out, why we have these 2 here. Any idea here? Okay, so think about it. Why? Basically, what I'm using is using a plus b squared is smaller than 2, say a squared plus 2 times b squared. So I'm using this kind of identity, and you can verify that this is true. Okay, so this is it. So then, okay, so this is for the variance term, or we have 2 times variance of reward plus 2 times variance, 2 times gamma squared variance of max at the next state. So let's focus on the max term, variance of max. Variance can be upper bounded by second moment. So I have expectation of just the second moment, right? So we have that. And then, so instead of, I want to get rid of that expectation. So what is random here? X prime is random here. But in order to get rid of it, I can take the worst case possible X prime. So I search in the space of all possible state and actions and take maximum of it. So that would be maximum over state and action of QT, X, and A. So that's what's happening here. And then next step is that I can upper bound maximum with summation. So maximum function is always smaller than the summation of that function. So what I'm having here is that, okay, so maximum of, say, f of x is smaller than summation of f of x. So this results this. So I replace it with the summation. So we get summation over state and action, qt, x, and a squared, which is the definition of the L2 norm. squared. So this gets this specific form. So variance can be upper bounded by squared L2 norm of Q. So if I put all these things together and assume that the reward distribution has a finite variance, sigma r squared, over, and I'm taking maximum over all state and action, then the variance of the noise term can be upper bounded by 2 times the variance of reward plus gamma squared times the norm squared of Qt. So if we could go back several slides ago in the stochastic approximation results, okay, here was the condition that we wanted to satisfy. So we wanted to show that the variance of noise is upper bounded by a constant C1 plus C2 times the L2 norm squared of that theta. We have the same form here. So we have the same form here. We have the Q, and we have this constant term. So if we choose C1 equal to 2 times sigma r squared, the variance of noise, and C2 equal to 2 gamma squared, the condition would be satisfied. And this is the noise condition. Other conditions we have already proved that are satisfied. So we can use that convergence result for stochastic approximation and show that, which results that Qt converges to Q star. Okay, is this clear? I think it's good to go through the proof again and go through the derivations. It's probably difficult to capture it. Okay, so question?
Quick question. If you go back to slide 62, when you're doing the verification, how do you go from the second last line to the last line? Like, how do you do expect? Is that an identity expected value less than equal variance?
From this one to this one?
Yeah, the second last to the last.
So which, right, so this is the definition of, okay, right. So let's see this part, like maybe, so I guess one question is, okay, so first I go through this step, and A would be RT minus RXT. So I get to this one, maybe I write it down. So I would get something like 2 times expectation of RT and there's a condition. So do you agree with this part?
Yeah. Yeah.
Okay, so, and is this the question why this is the variance?
Mm-hmm.
Okay, so because this is the kind of the definition of variance, if we notice what is this RT is, R is. So RT is a noise coming from distribution XT-AT. And the way we defined R, XT, and AT is exactly the expectation of that RT.
Okay. Oh, I see. Okay, okay.
So
yeah,
that's a definition of it.
Okay.
And for the second term, it would be, for this part, it would be one sample, like max Qt acts like a noise essentially. And this is, this part would be equal to expectation of that max thing.
Yeah, makes
so
sense.
That makes it variance.
Okay.
Good. Okay, so maybe, I think we are almost done with this. So let's finish it even though we're a bit, we haven't had a break at the usual time. Okay, so a few remarks. One is that the step size condition is state action dependent. So it was alpha t of xt at, or in the condition of Q learning. So the condition here was at of xt and at should diverge, and alpha t xt at squared should converge. So that's the condition which depends on state and action. So we don't have one learning rate, but we have multiple, the size of state action. So if there is a state action pair that is not selected at all, or only selected a finite number of times, not selecting at all is a special case of finite times, with finite being 0 here, then the condition cannot be satisfied. So if we go to state, say state 5, say, or some simplified, x1, a1, suppose we only visit at time 5, 25, 30, and 100, and that's all. So 4 times we visit it, and that's all. Then the condition that the learning rate at that state is going to be infinity, the summation of it is not going to be satisfied if alpha is going to be finite, because we are effectively, the condition would be alpha t x1 a1 over all t's. So we visit at time 5, 25, 30, 100. So it would be alpha 5 plus alpha 25 plus, well, just alpha 100 for that particular state. I'm not writing it. And if alpha t's are finite number, adding a finite number of finite numbers cannot get you to infinity. So you actually have to visit that state action pair infinite times in order to satisfy that condition. So for Q learning, to converge, there is this implicit assumption in the learning rate condition that says that in order for them to be satisfied, we need to visit each state and action pairs infinite number of times, and also choose the right learning rate too. I mean, we need to have both right schedule for learning rate and also visit that state action pair infinite number of times. So this means that if you just run a policy and follow a policy on your algorithm, it doesn't mean that Q learning should converge, because the policy may not take you to all state and action pairs infinite number of times. So, and this is actually interesting. Say, for example, if your policy is greedy, for sure you are not going to visit all state and action pairs infinite number of times. Why? Because the greedy action well, maybe for sure is not accurate, but very likely. Greedy action always chooses one action, and it converges to one action, and it doesn't choose other actions in that particular state. So for actions other than the greedy action, we don't have that condition satisfied. But then if we have, say, epsilon greedy, with epsilon that is non-zero, then if we get to that state infinite number of times, the actions at that state are all going to be chosen infinite number of times. So we are going to be okay. But again, epsilon greedy alone does not guarantee you to go to all state action, to all states infinite number of times. So for example, if this is your environment, so it's kind of, maybe it's kind of, say, if your agent starts here and never gets through this passage, for example, by some reason, maybe it's blocked. Maybe it's blocked. Okay, yeah. So if the doors between two rooms are closed, your agent always starts here. It never gets to this right region. So you don't have infinite number of times of visitation in any of the states here, which means that your Q value in this region would not converge to Q star in that region. So that's kind of intuition. Okay. The second part is, okay, some other remark is that state action dependence, okay, usually the Q-learning algorithm, if, for example, you look at, say, Sutton and Barto's book, or many other places, or even, I guess, the algorithm that I had on the first chapter and in the first lecture, the learning rate was just alpha t. It didn't have any dependence on state and action. So what happens? Like if we have that condition, we may not satisfy the condition required for convergence that I talked about today. But then if a single learning rate might suffice, if the agent happens to visit all state action pairs frequent enough. So for example, if it visits every m steps, and m being finite, like 100 steps or million steps, then that's okay. It's, again, the step size condition for each state and action would be satisfied. But the condition is that we visit them frequent enough. Okay, the other condition is that this is only an asymptotic. Okay, so other remark is that this is only an asymptotic guarantee. It shows that as time goes to infinity, when Qt converges to Q star. But this is just a limit result, asymptotic result. It doesn't say how fast. Like, does it go fast or slow? This result doesn't reveal anything. There are results showing, so this is kind of the result that we got from 90s, essentially. But more recent results, we have more recent results, because in early 2000s, or maybe even late 90s, we had some results that provide some kind of convergence rate for Q-learning. But this is not completely, it wasn't completely resolved, and there are more recent results in, I think, 2019, 2020, that provided better convergence rates for Q-learning. So this is relatively active area of research. It's for finite state and action pairs. So most people have finite state action MDPs. So most people focusing on large MDPs, and we have function approximation, which is the topic of the next lecture. But still there are questions even for the case of finite MDPs. And we still have new results. Okay, so I think that's all I want to talk about in this lecture. This part of this lecture, I will come back.